Okay, thank you. Yes, this is a project together with my PhD advisors, Johannes and Nadia, on score matching based on diffusion models. Okay, so this is a small teaser. So the project revolves around this, basically these two observations. On the one hand side, there is score matching, which is, you can consider it kind of an alternative to maximum likelihood, which can be used to estimate models that have intractable normalizing constants. But it actually does not perform very well for multimodal distributions. And this picture there gives you an idea that for this simple bimodal Gaussian mixture, these dotted lines are the scores, and they only vary on a set that has almost measure 0 for any distribution in that family. So whichever ground truth it is, you integrate the distances between two scores with respect to that measure. So the loss will always be flat. You will see that later in a picture. So as a result, these estimators can be very inefficient. And then on the other hand, diffusion models are known to perform really well when it comes to generating images, and images in general are multimodal, like come from multimodal distributions. And they are actually based on score matching. So we asked ourselves the question, why is this? Why does vanilla score matching perform poorly with respect to multimodal distributions, but diffusion models do not? And is there something in diffusion models that we can use to improve score matching? And if yes, can we show that this actually, that there are some guarantees attached to this? Okay, so I will, since this is very much a work in progress, I will speak more about actually the idea and the goals. Before this, I will give you some background on score matching and diffusion models, and then in the end, I will, we can look at a small toy example that kind of indicates that this estimator has some nice properties. Okay, so I already said this. The idea of score matching is the desire to estimate models that have intractable normalizing constants. This can arise in different situations. If you want to normalize a high-dimensional density, you have to compute a high-dimensional integral. This can be difficult. Different graphical models have the problem that the normalizing constant, computing the normalizing constant requires summing over all possible graphs, which is already infeasible for relatively small graphs and so on. And so score matching is based on this loss function, which is the Fisher divergence, and it's basically just an L2 distance between two scores. And in this literature, it's a little bit confusing because the author that kind of started this line of research, he wasn't a statistician. So this gradient with respect to the sample space, he called it the score, but it's not the classical score, which is the derivative with respect to the parameter. So if you then use this Fisher distance or Fisher divergence and you replace the measure at the expectation with the ground truth or the empirical distribution and the other one with the family that you want to estimate, then you define the score matching estimator as the minimizer of this loss. And since the score, as you can see at the bottom, the score function does not depend on the normalizing constant of the density. So as a consequence, the Fisher divergence doesn't either with respect to axis. Okay, so what can we say? Like, are there good things we can say about score matching? Yes. So it's under some assumption. It yields consistent estimators that are asymptotically normal. And if you make further assumptions like these functional inequalities like Poincaré or Log-Sobolev inequalities, you also get some form of guarantee. For example, this second one, you can kind of see that, or you could understand score matching to be a maximum likelihood estimator with some slack. So if the log-Sobolev constant is small and you minimize the Fisher divergence, you will also minimize the Kullback-Leibler divergence. But the thing is, these functional inequalities, they are kind of strong restrictions, and there are many distributions that are interesting that do not fulfill these, like mixtures or multimodal distributions. So yeah, it would of course be nice to be able to say something about the performance of score matching in more general families. And here, this is maybe a small reminder. These inequalities, or let's say, if you consider log-concave distributions, which are somewhat of a generalization of Gaussian distributions, that those log-concave distributions are usually unimodal and they have sub-exponential tails. So they are kind of nice distributions. Log-Sobolev and Poincare distributions that fulfill these two inequalities, they don't have to, it's not as strict as log concavity, but there still has to be some kind of concentration, and so unimodal distributions, multimodal distributions will often not fulfill these. Okay, and now I come to the problem that we are most interested in. As you said, it's right, there are other problems, but one problem is this one. So the Fisher divergence, it's actually kind of a weak notion of a distance between distributions. So it's a divergence, it's zero if and only the two measures are the same. But just because the Fisher divergence is small, this does not mean that the distributions will also be close to each other in a different distance measure. And this formally, this is kind of a toy example that shows this. If you take like two simple mixtures of two Gaussians with mean mu and minus mu, and you just have one that has the same weight on the two modes and the other one puts weight more on one than the other, then if you make an assumption on the mean mu, the total variation distance will be bounded away from zero. But if you then just send the means to infinity, the Fisher distance goes to zero. So even though these two distributions will clearly never be the same, whichever value of mu you choose. So this is kind of on the level of the loss function. But it appears that this has consequences on the level of the estimator in terms of its efficiency, and this is a result that kind of formally shows this. The authors constructed this exponential family, and then they basically showed this kind of a very rough sketch of their result. They showed that that there's basically a direction in which the covariance of this is actually the asymptotic covariance of the score matching and the maximum likelihood estimator, and the score matching estimator can have a much larger variance than a MLE, and this isoparametric constant, it's somewhat related to these functional inequalities that I talked about earlier. A distribution that has a large isoparametric constant, it needs to have let's say, a set on which there is some mass, and this set is surrounded by an area that has very little mass. So there's kind of some concentration of measure happening, but it's separated from the rest of the support with an area of very little mass. And this is exactly what happens with multimodal distributions if you have the modes sufficiently separated from each other. All right, so this is the observation. This is And this is kind of a simple family. This is a simple natural exponential family that is kind of extended in a particular way. This is not so important, but this can happen. All right, now a little bit on diffusion models. So diffusion models basically consist of these three puzzle pieces, let's say. So there's a forward process that turns data into noise. There's a backward or reverse process that inverts the forward equation. And this one then wants to use this to generate samples from noise. And in order to do so, one needs to estimate this score function in this reverse equation. And this can actually be done by a variant of score matching that is called denoising score matching, which I will say a few words about in a minute. And so this loss is a little bit more complicated than the regular score matching one. But yeah, it's nonetheless quite similar. And you can see here that basically this what this does is the forward process is used to turn the sample X into a Gaussian random variable if you let t go to infinity. And the loss is still the expectations which you take there are still tractable because the distributions, this conditional distribution at the innermost expectation is a Gaussian. So it's still easy to sample from these distributions and approximate these means. All right. Denoising score matching is a variant of score matching that was originally proposed to avoid this divergence term, which is also a little bit costly to compute in the vanilla score matching loss. And it's based on this idea of denoising autoencoders. And this middle version there, you basically replace the ground truth with a noisy one. And then you can make this tractable by showing this right equality there. And so it's basically an integrated version of the score matching loss. And I don't go into the details here, but there are both theoretically and empirically a lot of results for diffusion models. And this is a statement from a paper where they basically say that you can sample from any realistic distribution with these models. So we asked ourselves the question, can we use this somehow to make score matching better? And this is basically the idea. So you can steal, let's say, the first two puzzle pieces of the diffusion model. And what you actually do is you replace this score function in the original diffusion model by another score function. And what you actually do is there the initial condition for the forward process is that you assume that the data point is from the ground truth distribution. And here you assume that the data, like this score, is the score that you would get if you assume that the data point is from the family that you want to estimate. And because the Gaussian noise is added independently, that means that the f theta t is a convolution of the model density and the Gaussian density. So the whole loss now depends on a parameter, and you can also minimize this loss and get let's call it a denoising score matching estimator. And there's very little work on this loss, but these three things here have been shown. So you can actually show that this loss is more or less equivalent to the negative log likelihood. It differs only by a constant and the vanishing error. Then what I think is the most interesting one, some authors showed that it's asymptotically normal and it achieves the Cramer-Rao lower bound. And there is a finite sample guarantee, but it's for a Gaussian mixture with fixed weights, so they only let the means vary. So this is not really the case where score matching struggles. Score matching struggles to estimate the mixing probabilities, but not the mean parameters of the mixture. Yeah, so these are the goals that we want to work on. So first of all, we want to focus on this case on multimodal distributions. And then we would like to show that this estimator actually fulfills, some kind of guarantee, and that it recovers the true parameter with high probability. And then there are some interesting options where this base case can be extended. So one thing that is also has been studied a lot for diffusion models is to replace the forward equation with more general equations. This could be even more complicated, but one option is to replace this Brownian motion, this Gaussian noise that drives the process, with a different one, for example, one that has heavier tails. So maybe if the distribution is the multimodal distribution has very separated modes, using a driving noise that has heavier tails could increase the convergence speed, or you can introduce these functions f and g in the drift and diffusion terms. Then also one interesting aspect is this research area called generalized Bayesian inference, where people basically consider a generalized, what they call a generalized posterior, which is not based on the log likelihood, but on a loss function. And people have studied loss functions in this context that are similar to the score matching loss. And they had the same problem with respect to multimodality. So I think this loss function is a natural candidate to see how it performs in generalized Bayes. And then, of course, one important question, I think, is if this estimator actually retains the benefits that you wanted to have in the first place with score matching. So maybe all the denoising, all this integration that is happening in the loss is basically like computing a normalizing constant, and this is what you didn't want to do originally. So maybe the question is this like feasible for more complicated models? All right, and this is a small toy example. So we looked at this simple Gaussian mixture model. This is the plot that you already saw in the beginning. So the score functions only, these dotted lines, they only vary in the middle around the origin, but you will not observe this. So if you then compute the loss, it will always be zero, and you can see this there on the right-hand side. So the score matching loss, the ground truth parameter in that right-hand plot is 50%, but the loss is always zero, whichever parameter you choose. And you see that this denoising score matching loss basically imitates the negative log likelihood, which coincides with this statement that I showed you earlier. All right, and then for this estimator, if you make some assumptions, you can get this classical guarantee. Some of the details I have not worked out yet, but I think I will just give you an idea. So the score matching estimator is an M estimator, and that allows you to apply theory from M estimation. And there's this so-called convergence rate theorem for M estimators, which can be applied here. And in order to do so, you need to verify some assumptions. And actually, for this simple family, you can do this for this loss function. And you need to verify this curvature assumption that actually says that the loss behaves nicely around the true value, and a similar assumption for the empirical fluctuations. And if you do this, you then get a bound for the bound that I showed here. And since this family is so simple, so Gaussians are closed under convolutions. So this score function that arises in this loss is itself the score of a Gaussian mixture, and that's kind of a crucial part. So you can compute a closed form solution, and then you can actually verify these assumptions by explicitly differentiating under the integral and verifying these two conditions. And what you get in the end is that these two parameters in that rate, they are alpha and beta. You can verify that that this holds for alpha equal to 2 and beta equal to 1, which then gives this classical rate with respect to the sample size. The other dependencies on let's say, the mean value of the family, the mu, and also this this t at this integral with respect to t, this capital T, is also a parameter that you can, a hyperparameter that you can choose. These dependencies I have not worked out yet, because then the integral is actually a little bit more, like the loss function is actually a little bit more difficult to handle and figure out the exact dependency on these. All right. Yeah, this is it. So to sum up, the idea is, or we are interested in this poor performance of score matching for multimodal distributions, and we think that this estimator that basically takes the forward process and the loss from diffusion models is a promising approach to build more better score matching estimators, and we take this guarantee as a first proof of concept that you could actually show this. But then, of course, the question is, can this be extended to more general families? And if so, how could this be done? But I think the goals are kind of clear, because there's actually more open goals than things that have been finished already. So I think these are the main ones: the extension, the guarantees in general, the extension to the Bayesian setting, and maybe most importantly, if this is even computationally feasible in the end. Thank you.